our next speaker, last speaker for today, is Lénaïc Chizat from Paris Saclay. And Lénaïc is going to tell us about analysis of gradient descent on wide two-layer ReLU neural networks.
Thank you for the introduction. So in fact, I plan to attend this conference physically, but there was this weird quarantine rule for French people going to the UK, so I had to cancel the plans. But I wish I was with you, and I hope that you'll enjoy the conference. So this is joint work with Francis Bach. I'm going to present a paper that we have published at COLT 2020 last year, which is about wide two-layer neural networks. So in this short presentation, I will only talk about a single model. So let me present what it is about. So to keep things simple, I will only talk about one model. We consider a classification task where the input is x, y is the output, x lives in R to the D, and y is -1, 1, or R1. So it's just a classification task. And we are given n IID samples. We want to build a predictor such that its signs, so the sign of the predictor H, tries to predict the variable y. And the class of predictor that we will consider are wide two-layer ReLU neural networks. So this is a very specific parameterized class of predictors, which is written as follows in this example. So this is the sum of m simple function. M here is the width of the two-layer neural network. And each of the simple function, these functions phi, takes the input x, applies an affine transformation parameterized by the weights A, which I will call the input weights. Then we apply a nonlinearity, which is in this case just the non-negative part. And then we multiply by a scalar output B, which we will call the, a scalar quantity, which we will call the output weights. And so each of these functions, I will call it a neuron. And in each neuron is parameterized by the couple AB, which lives in R to the D plus 2. So notice this scaling factor 1 over m in front of the function, which will turn out very important because we will consider the training dynamics when the width of the neural networks goes to plus infinity, and the choice of the scaling here is important. In particular, this 1 over m is necessary to obtain a non-degenerate dynamics in the infinite width limit. And another aspect which is very important for this talk is that this function phi, I could consider other nonlinearities, but what's something which is very important is that it is too homogeneous in the parameters W, which means that when we multiply the parameters by some scalar R, we multiply the output by R to the squared because both the input and the output weights are multiplied. So that's our parameterized class of models to solve our classification task. And now the goal of the learning algorithm is to select these weights Wj so as to solve the task. I think I have a question in the chat, maybe. Oh, no, okay. And now the way we will select these weights is the standard way via empirical risk minimization. And in this talk, to simplify the analysis and following some previous work, we consider losses with an exponential tail. So this includes the logistic loss or the exponential loss. And we consider the unregularized empirical risk. That is a function of all the parameters of the neural network. This is a non-convex function in terms of the parameters of the two-layer neural networks, but often we observe good performance when training such models. And so we want to understand that. So we consider the standard gradient-based learning. We initialize the weights according to some distribution on the initialization. So here mu0 is some fixed probability distribution according to which we will sample the parameters of each neuron at initialization. And then we consider the gradient descent on the unregularized empirical risk. So it's important to notice that it's unregularized because we will be interested in the implicit or the algorithmic regularization. And here I consider the continuous time gradient descent dynamics, which is called the gradient flow, although that's not really important. We would obtain similar results with the gradient descent. But to simplify the idea, we consider the continuous time dynamics, and we want to understand how it behaves. So let me first start with an illustration of what we will look at. So here, this is a simple two-dimensional classification task. On the right side, we have the predictor space. So the black line will be the decision boundary, and I will show the training dynamics of gradient descent starting from a random initialization. On the left side, this is the parameter space. So each dot represents one neuron of the neural network. Since it's a two-dimensional classification task, the parameters of each neuron is in R⁴. So to obtain something that I can plot in 3D, I plot the input weight multiplied by the norm of the output weight. And the color here of the dot depends on the sign of B. And now there's something specific about when we train for a loss with an exponential tail, is that all the minimizers are at infinity. Typically, the weights, the parameters of the neural network will explode to plus infinity. And so to visualize properly the dynamics, here the unit sphere is at infinity. Okay, I've applied the hyperbolic tangent to the radial scale so that we visualize properly the dynamics. And here is how it looks like in parameter space, and here in predictor space. So at first, we have the neurons that move, all the parameters move, and little by little, we learn some predictor. And in the end, we observe something quite interesting, is that we find quite a simple predictor. It has a polygonal decision boundary. So that's what we see in predictor space. And in the space of parameters, this we have, although we had a lot of neurons at initialization, I think here it's 400, at the end, they have clustered into just a few groups. And this corresponds to this polygonal lines in the space of predictor. So the goal in this talk is to understand the performance and the properties of this predictor that we have learned. And of course, this is in general a too difficult question. So we need to make some assumptions. A lot of previous work has studied similar problems by making a stronger assumption on the training set or on the distributions according to which X and Y are sampled. But here in this talk, we'll take a different route. Instead of making assumptions on the data, we'll make some simplifying assumption on the model that we learn. And in particular, we will take its infinite width limit, which means that instead of having a finite number of dots here in the cloud of points that evolve in time, we'll consider an infinite number of points. And it turns out that this allows to simplify the dynamics and observe and obtain a sharp characterization of the predictor that we have learned after training. So first, I will recall a result, which is where our inspiration comes from this set of authors. Which is about linear predictors, or here more specifically affine predictors. So let's forget about two-layer neural networks just for this slide, and we consider training this linear predictor on an exponentially tailed loss with gradient descent. So these authors have shown that if the training set is linearly separable, which means that there exists some weight W such that H has the correct sign on all the training sets, then for any initialization W0, first they show that the gradient flow will escape to plus infinity. This is due to this tail of the loss, which never stops decreasing when we escape to plus infinity. And then they show that the normalized gradient flow, so when we just project it back on the unit ball, it converges to a L2 max margin classifier. So this is a solution to this max margin problem. The convergence is when the training dynamics goes to in the infinite time horizon of the training dynamics. So that's a result that we know about linear predictor. It has been extended in several ways for nonlinear models. And here is our, but to present the result for two-layer neural networks, I just need to introduce a certain notion of norm in predictor space, which is the one that will come out in the implicit regularization statement. So let me define two norms in the space of predictor. So norms on functions from RD to R, which are defined as follows. So we try to decompose our function H as somehow a sum of simple functions which are rich functions like this, an affine form composed with a non-linearity. Sorry, I have, okay. And over all such decompositions, using this function G, which represents the weights we give to each of the simple function, we define the F2 norm as the one with the smallest L2 norm, like the decomposition with the smallest L2 norm where so G is a function on the sphere, which parameterizes these ridge functions. And we similarly define the F1 norm as the one with the smallest, as the decomposition with the smallest L1 norm. So this corresponds to this switch from the parameter space view to the predictor space view, which Surya was describing in her talk previously. And so these two norms, they will define two different kinds of a priori or priors on the space of prediction functions. And to talk in a very rough terms, you can think as the F2 norm as a norm which favors isotropic smoothness. So it will be small for functions which are smooth in an isotropic way. And in high dimension, they need to be extremely smooth. So F2 is in fact a reproducible kernel Hilbert space. And the F1 norm, in contrast, so first, it's able to approximate functions which are smooth in an isotropic way, but it's also able it will be small also for functions which are anisotropically smooth, in the sense that they can have a lot of variations in a few directions if they are very simple in all the other directions. So F1 is adaptive to some anisotropy in the problem. So I will give a specific result which exploits this property in my talk. So now I'm able to present our implicit regularization result, which is as follows. So it will differ in some important ways to the ones I've presented about linear predictors. So now we are back to two-layer neural networks, and we have the following result. So assume that the distribution that we use to initialize our network is the following. Here, this means that the input weights are distributed uniformly on the unit sphere, and the output weights are uniformly -1 or +1 with equal probability. So this is just a specific example to fix ideas, but many other initializations could be allowed. In particular, the absolute scale of the initialization does not matter. Now we do not need to assume anymore that the training set is linearly separable, because two-layer neural networks with the ReLU actuation, they are universal approximators. So we just need to have a consistent training set. We just need to have the existence of a function that perfectly classifies the training set. And then there will be other technical and spurious assumptions, which I will briefly talk about later. But then under this assumption, we can show that the predictor converges to a F1 max margin classifier. So this means that if I consider this function, which will be the normalized predictor, so the actual predictor, it will be a function which diverges to plus infinity. But now if I renormalize it so that it has a constant norm, when I take the width m to plus infinity and the time t of the training to plus infinity, then the margin will converge to the max margin on the F1 ball, sorry, F1 unit ball. All right. So here the limits in t and m, they can be exchanged. So you can they can be interchanged. It does not really matter in which order we take the limits. So a few words about the proof technique and these technical assumptions. So what we need to assume, and you can see the rigorous statement in the paper, is that the infinitely wide dynamics. So we first need to define what it means to have a infinite width dynamics of two-layer neural networks, but then we consider the dynamics and we need to assume that the corresponding predictor converges in infinite time. So that's an assumption which is spurious. We would like to get rid of it, but so far we have not been able to. And then we can show this result. So maybe to compare it to previous results in the literature concerning these losses with an exponential tail. So there exists general statements that tell us that when we train a model with such a loss, we'll typically converge to critical points of the minimum L2 solution interpolator. Somehow that's what was what Surya was mentioning in her talk. But here we have somehow a stronger result because we have a global minimizer of some convex problem in the space of functions. And to obtain these stronger results, we really need to exploit the specific structure of these two-layer neural networks. And in particular, there is specific compatibility between the optimality conditions that we have for this problem and the dynamics of gradient descent, which is really specific to this two homogeneity property of these two-layer ReLU neural networks. So here we use this property, and there's also a fact that we use, which was we have found that it was coming from prior works, that when we initialize an infinitely wide two-layer neural network with enough diversity at initialization, then we are able to escape the neighborhood of spurious stationary points. So we combine all these ingredients to obtain this sharp characterization of the learned predictor. So a few more words about these results. So first, this max margin problem under the F1 norm, F1 ball, there is no efficient algorithm that I know solve this problem. In fact, it's very much related to problems that are known to be hard in high dimension. So I do not expect to have efficient algorithms in general to solve this problem. And here, this is purely a qualitative result. We do not know how large M must be, nor how large T must be. So it's really a qualitative result. And we know that in some cases, we would need an exponential number of neurons or an exponential time to obtain and to converge to this solution. But still, it gives us some qualitative hint as to what the gradient descent dynamics converges to in this setting. And another comment is that if we do the same training dynamics, but instead of training both layers of the neural network, we only train the output layer, then we can show, and it's a much simpler result that can be, in fact, a consequence of the results I've mentioned previously. We can show that we converge to a max margin classifier for the F2 norm. So we have these two types of implicit regularization, depending on whether we train both layers or just the output layer. So let us see what it looks like in practice. So I use a very simple synthetic experiment. So I consider a two-class classification task in 15 dimensions, and only the two first dimensions will be relevant to do the classification. So here I show the two first coordinates. So we see the two classes in blue and red. This is the training set, and all other remaining 13 coordinates will be irrelevant to do the classification. Okay. And so now we train our two-layer neural networks on this training set. So first, to observe what our result shows, here I plot the F1 margin after training as a function of M, the width of the neural network. And we observe that as the width increases, we converge to some plateau, which is and should be the max F1 margin classifier over the F1 ball, where we do not put any constraint on the number M of neurons of the neural network. So our theorem does not tell when we converge to this max margin. We just know that the black curve will converge to its maximum value. And here we observe that we only need 100 neurons to find the max margin classifier, but I expect that this will highly depend on the specific task at hand. And now let us look at the test error, whether we train both layers. So here, this is the F1 max margin classifier, or whether we train only the output layer. So here, this is the F2 max margin classifier. And we see that after seeing, here N is the number of samples in the training set, after seeing 500 samples, when we train both layers, we have almost perfect generalization error, like almost no test error. While when we only train the output layer, when we solve this kernel max SVM, we have a lot of large error rates after 500 samples. And here, this is really specific, again, to the synthetic example I've chosen, because there is a lot of anisotropy in the task. What we would like is that the neural network understands that only the two first coordinates are relevant to do the classification. But of course, the neural network does not know it at first. And here we see that when training both layers, it's able to exploit this structure. So there's someone who has his mic open. So please can turn it off. So here, this was a numerical experiment. And in fact, we can use the statistical theory to have theoretical results that goes in the direction of this this observation. So let me present a result of this sort. So we make assumptions somehow that captures the situation that I've presented in the synthetic experiment. We assume that the input X is bounded by R, and that there is some smaller rank, smaller dimensional projection of rank R, such that the interclass distance after this projection is delta of R, okay? So here in the previous example, delta of R would be, so R would be 2 because only we can make a projection of rank 2, and then delta of R would be the distance between these two, the two classes after this projection. And so R over big R over delta will be the complexity of the task. And the larger it is, the more complex it is, the more complex the task is. And so we can give the following generalization bound, which follows from standard margin-based generalization bounds, as well as some approximation results with the F1 norm. We can show that the F1 max margin classifier admits the following risk bound. After seeing n samples, it is bounded by 1 over square root n, so this is a standard rate, multiplied by the difficulty of the task to the power R. So R here is the dimension of the projection. So what's important to notice is that first, this bound is not, the goal is not to have the asymptotically optimal rate in terms of n, because here we have a task with two disjoint classes. And in fact, we can have much better rate asymptotically in n, but what we are interested in here is the dependency in the dimension. And here you see in the bound that the dimension D never appears explicitly. Often it can appear implicitly in the radius R. But here, this is a dimension-independent non-asymptotic bound. And this confirms somehow the good behavior that we observed in the numerical experiment. And a small comment is that when we learn in F2, so with this only training the output layer, we can have the same bound true, but only with R equals to D. It's just an upper bound that we can easily prove. Okay. So that's it for this, this discussion of the max margin classifier. Now I will just add a few comments, a few other directions, because I have maybe a little bit less than 5 minutes left. So first, here, everything I've presented in terms of optimization was non-quantitative. But it's interesting to know how fast we can expect convergence to happen. So unfortunately, it's too difficult. So far, we have no result that can tell us to make this implicit regularization result quantitative. But in some simplified setting, we were able to obtain some results. So in particular, if we fix the direction of the parameters of the input layer, so which means that the parameters of the input layers are vectors in, for each neuron, it's a vector in R to the D+1. So now assume that we fix its direction and we only train its magnitude. So it's a simplified problem, but still it's a non-convex parameterization of a linear predictor that we obtain in the end. And in that case, we can show a convergence rate in big O tilde of t to the -1/2 for a certain choice of step sizes. So here, this is a result that might only be understandable by specialists that have looked at this problem. But I'd like to mention that our proof technique consists in looking at, instead of looking at the empirical risk, we look at the gradient ascent or minus log of the empirical risk. And then we obtain some kind of a smooth margin of the objective. And what we show is that implicitly, when we do the gradient descent dynamics, we are doing some form of online mirror ascent on a sequence of losses that converge to the margin objective as the norm of the predictor grows to plus infinity. So that's the philosophy behind our proof. And it allows us to obtain a certain convergence rate. Okay, so that was a small comment in passing for quantitative results in terms of optimization. So do I have a few more minutes, or maybe we can switch to the questions? Otherwise, I can mention another result.
Yeah, go ahead.
Okay. So I'd like to conclude on on the last comment, which I think is a funny phenomenon, where we can see two implicit regularization along a single training dynamic. So let me explain. There is this phenomenon that we have heard a lot about recently in the past 2-3 years in the machine learning community, about which I like to call lazy training, or it's also called the kernel regime of neural networks training, which, and I will put it in my own words, it says that, in particular in this context, if I keep all the parameters equal, and if I increase the variance at initialization, and I decrease proportionally the initial step size of the training of the gradient descent. So if I increase the variance of the initialization, then we know that the model will behave like its first order expansion. So first order expansion in terms of the parameters over a significant time. And of course, the larger the variance, the longer the model will behave like its first order expansion. So that's the lazy training phenomenon. And what it means is that in this context of two-layer neural networks, each of the neurons will hardly move, but together they will produce a significant change in the space of predictor. So of course, everything here can be made quantitative, but I just want to remain at an informal level for this conclusion of my talk. And what we'll obtain is that the linearization, if we train the linearization of the model, will converge to some kernel max margin classifier, because the model will behave like a linear model. And this looks like it's a bit of a contradiction with what I've presented, because we look at the same training dynamics. But in fact, this regime here is transient in time. It's only at the beginning of the training dynamics. But still, the result that I've presented still holds. And in the end of training, we will expect to have this F1 max margin classifier. So let us look at an animation which shows these two behavior, which is exactly the same code that I've used to produce this animation and the previous one, except that I've increased the variance at initialization, okay? So let us look at the dynamics. Okay, at first, we see that the neurons, they do not move. The only movement we see is because I'm moving the camera, but otherwise, all the neurons of the neural network, they hardly move, but they have found a perfect classifier for the training data. And we see that we have a smooth decision boundary. So in fact, here, this is the max margin classifier in the tangent RKHS. And then when we continue training, the neurons, they start moving. And we continue, the predictor continues to evolve. The neurons, they start moving, and we converge to this F1 max margin classifier, which is exactly the same as in the beginning of the presentation. So that's what we observe. We have these two implicit regularization along the single training dynamics. So that's what I like about two-layer neural networks, is that we can still have quite a precise qualitative description of what happens. And I think it will be much more difficult for deeper neural networks to have all these type of results. So let me conclude for this talk with some open questions. Of course, making all these statements quantitative. So I expect that much stronger assumptions on the, at least some assumptions on the training data or the distribution would be necessary to obtain polynomial time convergence guarantees. And of course, another interesting question is to study deeper model in the infinite-wide limits. And here we are not yet talking about implicit regularization, but I think the question of what is the correct mathematical formalism to describe deep wide neural networks is still a question, an open question. So thank you for your attention, and I can take some questions.
Great, thanks very much. So we have, all right, Nati's posted a question to the chat.
All right. So yeah, I guess it's more.
Oh, great.
It's more of a comment, but also a question following it. So the optimization. So first of all, great, and the optimization problem is indeed provably hard. That you mentioned is probably hard. I'm wondering. So that's the comment. And a question related to that, I'm wondering if you think that the issue is the width or the training time. Like, do you think that it's possible to get with poly width actually solve it with super polynomial training time, or is it?
Yeah, so that's a very good question. So I think that this is a problem about the width. Like, we need a super polynomial width, right, because the lower bounds, I mean, some there are many lower bounds, and so I'm glad that you put this explicit reference to the hardness of these results. So the ones that I have in mind are also about a statistical query type lower bounds, where you know that, so the issue is that if you have a signal, for instance, which only depends on y dimension in some sinusoidal way, for instance, there is a result by, I forgot who, I forgot exactly where this result is, but if you have a signal which is oscillatory and only depends on one dimension, then it will hardly correlate with a random neuron in high dimension. And so this is an issue because at the beginning, it means you will get no information in the gradient which direction to move. And so the problem is that when we sample neurons in high dimension, they will almost surely not align with the actual direction we want to learn. So at least for sure, there is an issue about the width. We will need super polynomial width. And then about the time, it can be solved, this issue of time can be solved by modifying the gradient descent dynamics in some simple ways. So I don't think the true issue is about time. For instance, if we have an infinite width and choose a very small step size on the input layer, then we can show that maybe under some, we can show that we learn in polynomial time. So this is really an issue about the width. Yeah. So thank you for this is a very good question.
Thanks.
All right, so we're out of time. Please join me in thanking Lénaïc again. And thank you to all of the speakers today. It was a really fun session. So we'll see you all again tomorrow.